Good morning, students. So, welcome in next lecture of Math F 211 Mathematics 3. Presently, we are doing the section 16. If one solution is known, how to find the another solution. So, last time we have started this section, and I have told you we have to assume the second linearly independent solution as a y2 is equal to v into y1. Then we have computed the value of v as integral 1 upon y1 square e to power minus integral p dx with respect to x. So in continuation of that, let us have this question. Audio video is okay?
Yes, sir.
So in continuation of that, let us have this question. Find the general solution. Find the general solution of y double dash minus fx y dash plus fx minus 1 into y is equal to 0. So if you compare it with standard equation y double dash plus px y dash plus qx y is equal to 0, you will get px is equal to minus of fx and qx is equal to fx minus 1. So here by inspection you can observe we have the 1 plus p plus q is equal to 0. So if any coefficient satisfies this condition, then we say y is equal to e to power x is one solution. So let's say that is the y1. So y1 is equal to e to power x is one solution. So that is your known solution now. It will behave like a known solution. So now you have to determine the second linearly independent solution. So let the second linearly independent solution be y2 is equal to v into y1, where v is equal to what? Integral 1 upon y1 square e to power minus integral p dx with respect to x. So here we put the value of the 1, 1 upon y1 square. So e to power x square, so it will become the e to power 2x into e to power minus integral of minus fx dx. Then you have to integrate with respect to x. So it will become 1 upon e to power 2x e to power integral fx dx into dx. So it will come integral e to power minus 2x plus fx dx, right? Fx dx with respect to x. And we know that this is the v. So here we have this is your v. So what is the second linearly independent solution? Y2 is equal to v into y1. So y1 is what? E to power x and into v. So general solution will become yx is equal to c1 y1 plus c2 y2. That is c1 e to power x plus c2 e to power x integral e to power minus 2x plus fx dx into dx. So that is your final solution, where the c1 and c2 are the arbitrary constant. Now we have the short formula for this, whatever we have computed, the formula for the v. So that is your question from your book. For another faster approach, right? For the another faster approach to formula 3. Formula 3 is what? V is equal to integral, right? V is equal to integral 1 upon y1 square y1 square e to power minus integral p dx into dx. So that is your formula 3. So that v dash equal to y2 upon y1 dash is equal to w of y1 comma y2 upon y1 square, and use the Abel formula in section 15 to obtain it. To obtain it. So we have the formula of the V. So in this case, we know that what is the second linearly independent solution? In this section, what we have studied, that y2 is equal to what? V of y1. That we have studied y2 is equal to v of y1. So from here we can write v is equal to what? Y2 upon y1. So if you have to compute the v dash, so v dash will be the y2 upon y1 dash. So that can be written as y1 and y2 dash minus y2 y1 dash upon y1 square. So which is nothing, which is the determinant y1 y2 y1 dash y2 dash upon y1 square, or you can say it is the Wronskian of y1 y2 upon y1 square. So here we have the first part, v dash is equal to w upon w of y1 comma y2 upon y1 square. And in the section 15, in section 15, in theorem A, section 15, lemma 1, we have proved that w is equal to what? C e to power minus integral p dx, right? C into e to power integral p dx, and that is nothing, that is the Abel's formula. So in the section 15 lemma 1 we have proved this. So when we put this in our equation, so v dash in place of the w we can put c e to power integral p dx upon y1 square. So v will is what? V is the integral, right? Integral c e to power minus integral p dx upon y1 square with respect to x. So that is your v. So the same v you can find, right? Because it is only the constant multiple. So whether you if you compute the y2 is equal to v y1, in that c will merge. So exactly you can say that v is equal to what? Integral e to power minus integral p dx upon y1 square with respect to x. So that is your v. That is the formula 3 in this chapter. So here you have seen we have used the knowledge of Wronskian to determine this formula, right? So that we have covered in the lemma 1 of the theorem A in section 15. Clear this part? Now, so this section 16 is over. Now we have to move to the next section. So next section, section 17. So it is the homogeneous equation with constant coefficient. So what is the homogeneous equation? Presently we are talking only the ordinary differential equation, right? Ordinary differential equation. What is the nature? That is a linear in nature. Now we are talking for the homogeneous equation. So what is the general form of the homogeneous linear ordinary differential equation? That is the y double dash plus px y dash plus qx y is equal to 0. So this is the second order second order differential equation, and it is a linear or ordinary differential equation or homogeneous ordinary differential equation. Now instead of as a special case, if px is only the constant p and qx is only the constant q, so our equation will become y double dash plus py dash plus qy is equal to 0. So this is the what? It is the second order differential equation with constant coefficient, with constant coefficient, because here the p and q are constant, with constant coefficients, right? So now in this section we solve this type of the equation. So here we solve the homogeneous equation y double dash plus px plus px y dash plus qx y is equal to 0 under the special case when px and qx are constant. Let's say p and q. So our equation will be the this one, right? So let's say this is the equation number 1, y double dash plus p y dash plus q y is equal to 0. So now we say that let let y is equal to e to power mx be solution of first, right? It is the solution of the this equation first. Let y is equal to e to power mx be the solution of the first. Why we have taken the e to power mx? Because here we have the y dash and y. So in the exponential function, right, in the exponential function only has the property that after the derivative it remains the exponential. That's why we have chosen this as a solution. So from here y dash will become m e to power mx and y double dash will become m square e to power mx. So when we put these value in the given equation, our given equation will become m square e to power mx plus p into m e to power mx plus q and e to power mx is equal to 0, is equal to 0. So this will give you m square plus pm plus q e to power mx is equal to 0. So you know that exponential cannot be just 0, since e to power mx can't be 0, can't be 0, implies m square plus pm plus q is equal to 0. So this is nothing, this is the quadratic equation, this is the quadratic equation, right? Quadratic equation. So quadratic equation will come when we take the second order differential equation. If you take higher order differential equation, then you will get the higher order polynomial, right? Means as you increase your order of derivative, here the order of polynomial will also increase. So presently we are studying only the second order differential equation, but rule for the higher order will be the same, right? Whatever we will do here, the same, in the same fashion you have to proceed in the higher order differential equation also. So here presently we have the m square plus pm plus q is equal to 0. So if its discriminant will be the b square minus 4ac. So it is the p square minus 4q. Now depending over the nature of discriminant, right, we have the three type of the root. So what is the case first? Case first, when roots are real, when roots are real and distinct, when the roots are real and distinct. So when it is when the roots are real and distinct of the given quadratic equation, that is the p square minus 4q positive, right? So in that case what is the roots? m1 comma m2, let's we have the two roots. So it is the minus b plus minus b square minus 4ac upon 2a. So minus p, right, we have this equation. So minus p plus minus b square, that is the p square minus 4ac 4q upon 2a, upon 2a. So that is the root. So now here we have the two roots, right? M is equal to, we have the m is equal to, we have the m1 and m2, and m1 and m2 are minus p plus minus p square minus 4q upon 2. So now it means what the solution we have taken? Y is equal to e to power mx, we have taken the as a solution. So is solution of first, it means y1 is equal to what will become e to power m1x and y2 is equal to e to power m2x are the solution of first, because m we have taken as a m1 m2, and m1 m2 are minus p plus minus root of p square minus 4q upon 2. And if you check, if you check y1 upon y2, if you check its independency, so it will become e to power m1x upon e to power m2x and e to power m1 minus m2 into x not equal to 0. So when it is not equal to 0, so we can say y1 and y1 and y2 are li solution of linearly independent solution of the first. So the general solution will become y is equal to c1 y1 plus c2 y2, that is the c1 e to power m1 x plus c2 e to power m2 x. So that is the general solution for the case first, when roots are real and distinct. Now what can be the second case? Second, what can be the second case? Roots are complex. If roots are complex, so when we have the complex root, when the discriminant p square minus 4q is the negative, less than 0, right? If it is the less than 0, then we say we have the complex root. So in this case, m is equal to what we have, m1 and m2, and you know that complex root always exist, right? Always exist in conjugate pair, exist in conjugate pair, exist complex root always exist in the conjugate pair. So that is equal to a plus minus ib, a plus minus ib. So and we know that y is equal to what? E to power mx b solution, b solution of first. It means y is equal to e to power, a plus ib, a plus ib, and let's say y1, and y is equal to, or y2 is equal to e to power a minus ib are solution solution of first. But in general, for the differential equation, we require the real valued solution, right? Here we have the complex valued solution, that is not of much use. So this can be written as y1 can be written as uh, e to power mx. So it is the mx, so this can be written as e to power ax and e to power I bx. This can be written as e to power ax and e to power minus I bx. And what is the value of e to power bx? Yes, anyone? What is the value of the e to power bx? Yes, anyone?
Cos bx plus I sin bx.
Yes, by the Euler's formula, it is the cos bx plus I sin bx. And here we have the e to power ax, and by the same formula, it will be the cos bx minus I sin bx. So here we have the y1 and y2, y1 and y2. So if you do the, now if the we have the two solution, their sum is also solution, their subtraction is also solution, constant multiple is also solution. So if you do the y1 plus y2 upon 2, so y1 plus y2, what is the y1 plus y2? E to power ax, then we have the cos bx plus cos bx, that is the 2 cos bx upon 2. So here we have the cos bx, right? Cos bx is also solution of first, is also the solution of first, means sum and subtraction of the two solution is also the solution. Similarly, and constant multiple of the solution is also the solution. That's why we are saying that y1 plus y2 upon 2 is equal to e to power ax cos bx is also solution. And here y1 minus y2 upon 2 eta, it will be the e to power ax, and y1 minus y2 means e to power ax plus eta sin bx plus eta sin bx, that is the 2 eta sin bx, and divide by 2 eta, so 2 eta and 2 eta cancel out, so e to power ax, and it will become the sin bx is also is also solution of first, is also the solution of first. So let's say now this is the y1, let, now this is the y2, let, right, let's say y2. So now if you check y1 upon y2, y1 upon y2, so what you will get, y1 is equal to e to power ax upon cos bx upon upon e to power ax sin bx. So it will be the cot of bx not equal to 0, right, not equal to 0, implies y1 and y2 are li solution, right, li solution of first. If the y1 and y2 are the li solution of the first, then y is equal to c1 y1 plus c2 y2 be general solution, be general solution of first, general solution of the first. So it will become c1 e to power ax cos bx plus c2 e to power ax sin bx, or this can be written as e to power ax c1 cos bx plus c2 sin bx. So this is the general solution for the second order differential equation when the roots of the auxiliary equation. So this is also known as the auxiliary equation, auxiliary equation. So roots of the auxiliary equations are complex. At that time we take the solution as a y is equal to e to power ax c1 cos bx plus c2 sin bx. Now what can be the third case? What can be the third case? Third case will be the when roots are when roots are real and equal. When roots are real and equal, then what will happen? Means when it is possible, when the d is equal to discriminant is equal to p square minus 4q is equal to 0. So at that time m is equal to m1 is equal to m2, right? M1 and m2 both are the same, equal and real, and it is equal to minus p upon 2. We have the root what? Minus p plus minus p square minus 4q upon 2. So that is equal to 0. Discriminant is equal to 0. So here we have the m1 is equal to m2 is equal to minus p by 2. And we know that y is equal to what? E to power mx b solution of first. So what you will get? Y is equal to e to power m1 x b solution of first. So you will get only the one solution. So how you can determine the second solution? You have only the one solution. How you can determine the second solution?
We can find v of x.
Yes, we can find the v of x, or we can use the whatever the theorem we have studied in the section 16. So let second Li solution of first be y2 is equal to v of y1. V of y1 clear, and where v is equal to what? Integral 1 upon y1 square e to power minus integral p dx, right? Integral p dx into dx. And what is the y1? E to power m1x, e to power m1x, and e to power minus what is the px? What is the px? In the px we have seen we have to write the stand is in the standard form. So already it is in the standard form. Our equation is this one. Our equation is this one. So here the p is what? Small p, a constant. So in this case, it will become e to power integral p dx into dx. So p dx into p dx will become, now what is the value of the m1? What is the value of the m1? m1 is equal to the minus p by 2, minus p by 2. So this will become e to power minus uh, 1 minute, it's square. So minus p by 2 into x and whole square e to power minus e to power minus p p and x, px into dx, px into dx. So it will become integral 1 upon e to power minus px e to power minus px into x into dx. So it will become integral dx, that is your x. So that is the v. So y2 will be the what? V into y1, that is the x e to power minus e to power m1 x, e to power m1 x, right? That is the our y2. So the general solution general solution will be yx is equal to what? C1 y1 plus C2 y2, C2 y2. And one more thing you can check, because and here already we are using the section 16, right? So need not to check, but if you want to check you can check also. Y1 upon y2 is equal to, it will be the y1 is what? E to power mx upon y2 is what? X into e to power mx, that is the 1 upon x, not equal to 0. So we can say y1 and y2 are the li. Means in the section 16 during the derivation we have already assumed this thing, so need not to check. So here the general solution is the yx is equal to c1 y1 plus c2 y2, that is the c1 e to power mx plus c2 c2 x into e to power mx, or you can say e to power mx c1 plus c2x, that is your general solution when we have the equal roots. So we have discussed all the three cases. Any confusion, any doubt, anything you want to ask, revisit? In the theory part, anything you want to ask? Clear? So now, so all these things we have covered. So here first is the case first, when we have the distinct and real roots, right? So at that time, the general solution is the y is equal to c1 e to power m1x plus c2 e to power m2x. Second, when we have the complex root, right? Complex root, at that time, we take yx is equal to e to power ax plus c1 cos bx plus c2 sin bx as a general solution. Case third, when we have the equal roots, so at that time we take the general solution as c1 e to power mx plus c2 x into e to power mx, right? So that is that much derivation we have done. Let us have some question depend over this. Find the general solution of y double dash plus 6y dash minus 6y is equal to 0. So here we have the equation y double dash plus y dash minus 6y is equal to 0. So in this case, you can see that small p is equal to 1 and small q is equal to minus 6. Both are constants. Both are constants. So you can say second order differential equation with constant constant coefficient. So for such equation, let y is equal to e to power mx be, let's say it is 1, be solution of first. So y dash is equal to m e to power mx, y double dash is equal to m square e to power mx. So our equation will become m square e to power mx plus m e to power mx minus 6 e to power mx is equal to 0. This will become m square plus m minus 6, right, e to power mx is equal to 0. Since e to power mx cannot be 0, this implies m square plus m minus 6 is equal to 0. So from here, this is the quadratic equation. M will come 2 and minus 3. So 2 and minus 3 means they are the real and distinct. So this implies y1 is equal to e to power mx or m1x, that is the e to power 2x, and y2 is equal to e to power m2x, that is the e to power minus 3x. So from here we will get the general solution c1 y1 plus c2 y2, that is c1 e to power 2x plus c2 e to power minus 3x. So that is your solution of the given differential equation. General solution of the given differential equation. Now you have to find the general solution of y double dash minus 6y dash plus 25y is equal to 0. If you have to determine the general solution of y double dash minus 6y dash plus 25y is equal to 0. So it is what? It is second order differential equation with constant coefficient. Right? We have this equation. So let y is equal to e to power mx be solution of first, then the auxiliary equation will come m square, from here m square minus 6m, directly you can write minus 6m plus 25 is equal to 0. So when we compute its root, so m will come minus b 6 plus minus b square 36 minus 4ac minus 4ac, so 100 upon 2a, so upon 2, so that is the 3 plus minus 4 iota, right? It is the 3 plus minus 4 iota. Means if you compared with the whatever we have written in the derivation, so a plus minus iota b. So a is equal to 3, a is equal to 3, and a is equal to 3, and b is equal to 4. So for such, the general solution, will be yx is equal to e to power ax c1 cos bx plus c2 sin bx. So what is the a? E to power 3x c1 cos of, what is the b? That is the 4. So cos of 4x plus c2 sin of 4x, where c1 and c2 are arbitrary constant. So in this way, you can write the general solution of the second order differential equation with constant coefficient when its auxiliary equation has complex roots. And you know that complex roots always, for the quadratic equation, complex roots always exist in the conjugate form or conjugate pair. If someone is asking something, if you have the doubt, please stop me and ask. Now, if we have 4y double dash minus 12y dash plus 9y, 9y is equal to 0. If we have 4y double dash minus 12y dash plus 9y is equal to 0. So this is what? This is the second order differential equation with constant coefficient. With constant coefficient. It is the second order as well as the what? Linear and homogeneous. Linear and homogeneous. So for these equation only we can apply this method. So let y is equal to e to power mx be solution of first. So auxiliary equation, either you do completely or directly you can write. So auxiliary equation will come 4m square from here, 4m square minus 12m plus 9 is equal to 0. That will be your auxiliary equation. So what is the value of the m? Minus b 12 plus minus b square 144 minus 4ac. That is the 144 upon 2a. Right? So here we have the, so this will cancel out, discriminant is 0. So 12 upon 8, 12 upon 8 means it will become the 3 by 2. M is equal to 3 by 2 and 3 by 2. So it is the real and equal. So y1 is equal to what? Y1 is equal to e to power 3 by 2, or y1 is equal to e to power mx is equal to y to power 3 by 2 x be solution of first. So one solution is known. You have to determine the another solution. So either you can go with the derivation, or directly you can say y2 is equal to what? X into e to power mx. X into e to power mx, that is the x e to power 3 by 2 x. 3 by 2 x be another Li solution of first. So general solution will become yx is equal to c1 e to power 3 by 2 x c1 y1 plus c2 x e to power 3 by 2 x c2 y2 be the general solution. B. General solution. So in this way, we can solve second order differential equation, right, with constant coefficient if its auxiliary equation has equal and real and equal roots.
So,
Yes,
if you directly use those standardized formula,
yes,
then in
directly you can use. Directly you can
you
use.
have to write a statement that by using these standard formulas, this is the answer.
Huh, directly you can use.
Okay, sir.
Find the solution of the following initial value problem. Right? Find the solution of the following initial value problem. So problem is y double dash minus 5 dash plus 6y is equal to 0, and condition are y1 is equal to e to power 2, y1 dash is equal to 3 e to power 2. So when we have the two condition at the same x naught, at the same x naught, then we say it is the initial value problem. Means initial value means at the initial point. So here we have the initial point x naught is equal to 1. So that is known as the initial value problem. And here we can observe what is this? This is the second order differential equation with constant coefficient. With constant coefficient. So what we assume, let y is equal to e to power mx be solution of the first. So auxiliary equation will come m square minus 5m plus 6 is equal to 0, and their roots are 2 and 3. So we can say they are the distinct and real. Distinct and real. They are the distinct and real. Clear? M is equal to 2, comma 3. So from here, what is the general solution? Yx is equal to c1 e to power 2x plus c2 e to power 3x be general solution. Be general solution. Now, if if right, this is the general solution. So now what is the condition is given to you? That y1 is equal to, or before that you compute the y dash. So y dash will come 2 into c1, 2 into c1 plus 3 into c2 e to power 3x, 2 into c1 e to power 2x plus 3 into c2 e to power 3x. Now condition is given to you when x is equal to, when x is equal to 1, when x is equal to 1, y is equal to e to power 2. So that we have written here. When we put x is equal to 1, so this is the e to power 2. So it will become c1 e to power 2 plus c2 e to power 3. When we have the x is equal to 0, y dash is given to you 3 into e to power 2. And so in this equation, when we put in this equation, you will put, so you will get the 3 e to power 2 is equal to 2 c1 e to power 2 plus 3 c2 e to power 3. So when you solve, you will get c2 is equal to e to power minus 1 and c1 is equal to 0. So in the given equation, you will put the value of the c1 and c2 as 0 and 1 upon e. You will get the answer as e to power 3x minus 1. So that is your now particular solution. So if conditions are given to you, if initial values at initial point or at initial value, if value of function and its derivative is given to you, you will get the unique solution, right? And it is free from the arbitrary constant. So solution is free from the arbitrary constant. That arbitrary constant's value you have computed from the given condition. Now, it is not necessary always you have the second order differential equation with constant coefficients. Sometimes you have to reduce into that form. So that is the another question. Solve equation. It is in the means not in the theoretical part. It is in the question form, but it is very important. So solve equation x square y double dash plus p x y dash plus q y is equal to 0, where p and q are constant, is called Euler's equation, or the Euler's equidimensional second order differential equation, right? Euler's equidimensional second order differential equation, so that change in independent variable given by x is equal to e to power z, transform it into the into an equation with constant coefficient, so here the what is given to you, x square y double dash plus p x y dash plus q y is equal to 0. So in this case, this p is the constant, this q is also constant, and this in the standard form, if in the standard form you will write, so it will become the y double dash plus p upon x y dash plus q upon x square y is equal to 0. So in this case, this will be the px and this will be the qx, and this is known as either you can say this Euler's equation, or Euler's equidimensional equation, or in the standard form, this is the Euler equation. Now it is given to you. In this, you assume let x is equal to e to power z, right? We will change the independent variable from x to z. So let x is equal to e to power z, or you can say z is equal to ln of x. If you take the natural log on both sides, so z is equal to ln of x. So from here, if you compute the dz by dx, you will get the 1 upon x. 1 upon x. Similarly, here you will get the, now if you have to compute the dy by dx, what is the meaning of the dy by dx? Dy by dx is the dy by dz into dz by dx. Dy by dx can be written as dy by dz into z dz by dx. So because here if you cancel, you will get again the dy by dx. And what is the value of the dz by dx? That is the 1 upon x. So 1 upon x dy by dz, right? Dy by dx is equal to 1 upon x dy by dz. Clear? So this will give you x dy by dx is equal to dy by dz. So one thing you have computed here. Then if you have to compute d2y upon dx2, d2y upon dx2, from here if you compute the d2y upon dx2, so by parts if you will do, so what derivative of the 1 upon x will be the minus 1 upon x square and dy by dz plus 1 upon x dy dx of dy by dz, dy dx of dy by dz, that can be written as 1 upon x dy dx of dy by right. So 1 upon x and dy by dx. So this can be written as dy dz of dy dz and dz by dx. So what will happen? This dz will this cancel this dz. So again you will get the dy dx of the dy dz. So this can be written as 1 upon x d2y upon dz2, d2y upon dz2 into dz by dx, and dz by dx is what? 1 upon x. So this will become 1 upon x square d2y upon dz2, and it is the minus 1 upon x square dy by dz, right? Dy by dz. So that is the d2y upon dx2. So from here you will get the x square d2y upon dx2 as a minus d by y dz plus plus d2y upon d2y upon dz2. So what is the first equation? First equation is the x square y double dash. X square y double dash, it means x square d2y upon dx2, that can be written as minus d by y dz plus d2y upon dz2 plus. Now second is px y dash, right? P into x y dash. So x into y dash we have already computed. X into y dash. X into y dash is what? It is the d by y dz. So it will become p p d by y p d by y dz plus, here we have the, in the equation here we have the qy is equal to 0. So here we write the plus qy is equal to 0. So this can be written as d2y upon dz2 plus p minus 1 d by y dz plus qy is equal to 0. So it is what? It is the second order, second order differential equation with constant, with constant coefficient, and independent variable are independent, independent variable, independent variable is z instead of, instead of x, instead of the x. Here we have the independent variable z instead of the x. So now you have converted your non means second order differential equation without constant coefficient into the second order differential equation with constant coefficient. Only just you have changed, just you have changed the independent variable from x to z by the substitution x is equal to e to power z or z is equal to ln x. And this is very important question. It is known equation, it is known as the Euler's equation or Euler's equidimensional equation. So in next class we continue. Why we have the p means second order differential equation with the constant coefficient? P is what? Constant. So p minus 1 is also constant, q is also constant. So it is the second order differential equation with constant coefficient. So in next class we continue. So derivation is over. In next class we do the question.
So can you move scroll up a bit? Yes, settle here. Thank you. Okay, sir, done.